Okay, so we have here, and then this will be, we can write, or let me just stop until here, okay, just to show you that this was the last result of the cross product. Okay. Or if we want to maybe write in the final terms, okay, this will be the result. So this what the Jacobian transformations, okay? This part, or perhaps here also okay. So Jacobian transformations given by, we have the x, which is function uv, so which means that we can find relation. It's not always uv, it can be any variables. Like example, we have the polar r theta that we can prove with Jacobian that it is true. So basically we have the x, we have y. They're both of this x, y, they are related with the uv. So basically, this is one thing I need to emphasize, is basically this terms is the one that we need to multiply so that the area in the double integrations for s and r, they will be equal. Okay. So suppose that you have the double integral and you have xy, but when you see the graph, it seems impossible to be worked on. So what you can do is basically, if you can find relations between some variables, and you can perhaps develop a new variables, and then you can supposedly transform this xy into something that is quite easily to be followed. For example, like the one that I showed you at the beginning, that we have like something that is not really easy to be followed for the geometry, but then you can transform that into a rectangle, which is very easy to follow, easy to draw, easy to calculate. So you could transform that, calculate the area, and you need to multiply with the Jacobian value to make it equal. Okay. So that's how. So this is a additional multiplication, scalar multiplication, or perhaps additional value that need to be multiplied. And then with the same assumptions and with the same results, we can also, when we have the delta A that is supposed to be in the last terms of the double integrals, which will we have the dA or delta A, we could also transform that delta A approximately using this Jacobian. Sometimes we write the Jacobian as this, and we need to multiply with the delta U, delta V. So this is something that we need to add, okay? And then the rest will be changed. Okay? And because it's changed to delta U and delta V, then we have a new variables to be computed in our double integrals. Okay? So how to make this happen and how to compute technically, okay? So technically in practice. So basically you have x equals something related to uv. So x is function uv. You have y function of uv. So first, if it is not given, or maybe it is intrinsically given, but you need to find the relation. So find out the relations first. Find the relation x with uv, y with uv, solve, and then make sure that it's on the x equal u and v. Okay. Y also equal u and v. Partially derive both of them with respect to u and respect to v. And then plug it into this Jacobian, compute this, compute the determinants, and you get the Jacobian. Okay. And because this is a double integration most of the problem, so you are most likely to have Jacobian on 2 by 2 determinant matrix. So if you have 3, you have 3 by 3, but I don't think I will give that 3. It's possible, 3 by 3 matrix, find determinant, but I don't think we have enough time for that. So I will just focus on 2 by 2 for double it. Okay. Maybe just a quick proof or quick recap or of what we have in the Jacobian, how technically we are going to take it. So okay, so this is just a summary, basically what we have before. So from S to R, and since this is, we can approximate, and since it's really small, we can make it the tangent vector will be equal with the vectors that's supposed to be the sides of parallelogram. And that's why we can have the cross product, which result in the Jacobian. Okay? So the Jacobian is actually results from the area of parallelogram of our vectors that's supposed to be in the sides here. Okay. And the assumptions is that sides of the vectors, they are approximately equal to its tangent. Okay, its tangent vector. Okay. Okay. And this is all the assumption that we might need, that the Jacobian should be non-zero, and then the T maps the region in the UV plane into the region R in XY plane, and then continuity, all that things should be also included. And type 1, type 2, I don't think you need to be defining which type. This is just to show you which functions that we deal with. Type 1 is for function of x, y function of x, and 2 is for x function of y. Okay, but I don't think that's important. And then suppose the P is 1 to 1, and except for on the boundary, then we have this transformations. Okay. Okay, now on the right side here, I have also a picture on another transformation. And suppose this is a transformation on polar. Okay? So we transform the r and theta, and also we have the x and y. In xy, we have this a polar curve. But what we want is, can we transform this into that which is basically geometrically easier to see and easier to be computed, okay, rather than this polar, right? And we can start by taking the conversion of polar, with r or x is r cosine theta, and y is r sine theta. Okay. And we are transforming through the Jacobian. So Jacobian xy is something that we have, and this one is something that we transform to, or you could say the image, okay, the image of. So we can write this as transformations, cross product, or determinant of 2 by 2 matrix. So D of partial x, partial r, partial x, partial theta, and then partial y, partial r, partial y, partial theta. Which means we are going to partially derive x with respect to r, which means this. So this will be, sometimes we are write x and then subscript r, the same thing. This is partial x, partial r. We can write this as, this is just a cosine theta, right? Or let me just write directly in the equation, and I will explain along the way. So partial x, partial r will be cosine theta. Partial x, partial theta, which means we are partially derived with respect to theta. This will be r sine theta. And then y, we take the same, oh, sorry, this should be minus sine theta. And then this will be r cosine theta. and then take the value, cross multiply. We have r cosine squared theta minus r sine squared theta, which this could be r cosine squared theta plus sine squared theta, which is equal r. And this is practically when we have the double integrations supposed to be like r, and then this is the xy. Suppose that dx dy at the end, or dy dx the same, equal, we transform to s with the function being converted. X will be r cosine theta and y is r sine theta. Multiply with the Jacobian, which is, let me just write the Jacobian here. And then this will be changed to dr d theta. And then from our calculations and from our assumption here that the theta will be from alpha to beta, the r will be from a to b, suppose, and this will be f r cosine theta, r sine theta, and the Jacobian is r dr d theta. The same thing that we did in the double integral polar, if you remember. Okay. So that's why this r comes around. We can also prove it into with the Jacobian value. Okay. So this is the Jacobian for the polar. Okay. Okay, any questions? So that is the Jacobian. So remember that how we should transform is basically first we need to find the relations for x, y with the other variables that we want to transform. Okay. Sometimes the question or the problem will give you maybe implicitly information with it. Like for example, maybe the point in the graph that you need to draw the graph first and then to find the linear equation, or perhaps another equation that is drawn from the graph, and then you can conclude the relation between x and x, y, and uv, maybe. Or maybe sometimes it will also give like a direct information, like, oh, you have these transformations, and then you need to calculate this, and basically you can transform base this on this Jacobian, and then you have this. Okay, maybe I have one example here and also some questions related to this. So this is a type of question in Jacobian. If you would like to see this one here. So sometimes it's given you the direct transformations like this. So when you have this, you can directly write a Jacobian using the partial. So partial x, partial u, partial x, partial v, and then the for y, u, v, and then take the determinants, and you get the Jacobian value. But then you have the points that you need to know the endpoints of your integrations, right? So you need to also follow that. Okay. I think we are going to take a break for next part. Will be, I think, overview from the previous part. Okay. Double integral as the iterated integral for the given functions and region D. So region is basically the graph, and the function is they have their f on each one of the graph, right? So let's say number 8, we have functions x plus y. Okay. So what should we do for this 8? Or let me give you a couple minutes to try first, okay? Just a couple minutes. Since on your TA class you will have a quiz, so I hope you can try now. Okay? If you don't have those motivation, maybe you will feel lazy and you do nothing. Should we start with 8? So I believe this is should we start with the linear equations that you can try for those triangles. So you can start here. What is the equation? And you can start here. What is the equation? You have the points. This is 2, 0, 0, 0, 1, 1. Start finding the solution. And I think because the triangle, they have the same proportions. So the slope for the other one will be the minus of the other one, right? For sure. So if this is 1, it should be negative 4. So you can also use that. And put into the linear equations. Okay, so perhaps we could start with, so we have the point here. So we know that the gradient here is 1, gradient here is -1. Like I will just write the line equations will be y minus, this is 2, 0, right? Oh, because it's 0, so I will just write y equal -1 and then x minus 2, or y is negative x plus 2, or x 2 minus y. Okay, so if you want to write in terms of x, you could do that. If you want to write in terms of y, you could also do that. So this can works both ways, and it will result the same. Okay? Either you start with dx dy or dy dx. It should be okay. It's up to you which one you prefer. So let me write in terms of dy dx. So suppose this is dy dx, or maybe dx dy. Maybe let me do dx dy first. So maybe here, number 8, or let me copy this. Okay, let me copy and let me erase this stuff here. Let me write on this part. So number 8. So it should be written as this is d, this is x plus y. I suppose this is dA. Okay. So I will, let's say, evaluating the outside will be dy. So dx dy. So let's say dx dy. If we start from this, so this one is y equal x, or x equal y, or let me write it with x equal y, and this one is x equal 2 minus y. So I will take the y from 0 to 1 for the constant, and then x will be from this to that. Okay, from x equal y into x equal 2 minus 1. Okay, so we can write that in this one will be 0, 1, and then x equal y, and then x equal 2 minus y, right? And then you can solve it. And basically you can solve the first one is taking the integration with respect to x. So half x squared plus xy, input the y and 2 minus y, and then you still have dy. And then slowly write down the substitutions. So 2 minus y squared over 2 plus 2 minus y, y, and then minus half y squared plus y squared, and then dy. Okay, and then we can easily see that this one will be 3 over 2, this is 3 over 2 y squared, minus, this will be 2y minus y squared. That will be 4 minus 2y plus y squared, divided by 2. This will be 2 minus y plus half y squared. Okay. Oh, wait. I did something wrong here. Should be not 2, should be 4. It should be 4 minus 4y plus, divided by 2. This is 2, this is 2y plus half y squared. So this is plus. So I will cancel this with that. And then plus should be half y squared minus y is minus half y squared. Minus 3 over 2 will be minus 4 over 2, which is minus 2y squared. So this will be 0, 1, 2 minus 2y squared dy. And again, take the integrations. 2y minus 2 over 3 y cubed. Okay, 2 minus 2 over 3. 6 minus 2 is 4, so 4 over 3. So that's for number 8. Okay, if you would like to take it into dy dx, I think also possible. Okay, let me write, but maybe you need to split the double integral. Okay. You can also write, so if you write the x plus y, suppose that you want to write dy dx like this. If you see this graph here, maybe let me copy and write here. Now, if we want to start from x, then if we say we start from x equal 0, it could be, but I think it's better to take this into two triangles like that. So the first one will be 0 to, let's say this is 1, right? 0 to 1 for x. And then since we have y equal x, and then y equals 0, so y will be start from 0 to x. This is for 1, okay? And then we have 2, this one. We could take this one is, y is, I forgot the equations. Where is x, y is 2 minus x, y is 2 minus x. Okay. So for 2, we could get the x will be from 1 to 2, okay? And then y will be from the 0 to 2 minus x. Okay, so you can have this. First is this. But I don't think this will be less complicated than the one before we compute. So you could also take this approach. But I'm not suggesting using this one. Okay, I'm suggesting because you could see easily from this y when it will take the whole area, right? From 0 to this one here, and then x will be from this to that. I think that's much better. You do it in one calculation. Okay. But if we would like to take the dy dx, I think also possible. The problem is because we have, in the middle we have this, so if we combine, there's a problem at this point. So that's why I need to split out. Okay. Okay, if you have chances, try other question as well. Okay, so that you can have much more ideas and perhaps familiarity with the process. Okay. I think the next quiz will be mostly the double and then perhaps polar. I think no triple. Okay, only double and perhaps polar. Okay. And let's get into other questions. Any requests? Which one we need to take? Any requests from this, or you want to try other, like this one, or from here? Between this and this, which one? 27, which is 27. We have double integral d 2x minus 1 dA. D is bounded by the circle with center, the origin and radius. We can work it in xy or in polar. But if we would like to work it in xy, I think we could also work this. Okay. So let's take number 27. Okay. Okay, because it's quite simple, and then I believe that we could work on directly. Okay, so let me check this out. Okay, so D is bounded by circle with radius 2. So it will be x squared plus y squared equal to. So if you work with xy, we have y plus minus 2 minus y is 2. Should be 4. Okay, 4 minus x squared. So this part on the top will be the positive, and the one on the bottom will be the negative. Okay. And then if we take this negative 2 and 2, so if we take the x as a outside integration, this is negative 2, 2. This will be 2x minus y, and then dy dx. Okay. I think you could try solve it, but another approach is just take the polar. And just take the polar. So taking the polar means that we have radius from 0 to 2, and theta will be full circle. So we can transform this into 0 to pi. This will be 2r cosine theta minus r sine theta. And this will be r dr d theta. Okay. Yes?
Should we use symmetric or use from 0 to
In this part, unless you can prove it, I think it should be okay.
Is a circle in origin and the center? Can we just divide each quadrant so we got 4 of?
Yeah, 4 and then 4 area, right?
Yes, and then use symmetry.
Yeah. The same.
But it's in the same loop. If we take from 0 to 2 pi, can we get like the value it minus itself so we can evaluate the wrong area?
Yeah. Also okay. Sometimes both works, sometimes not. But I would like to say perhaps sometimes there are some polar that you need to make sure the intersections. But for this, because it's a full circle, I think symmetry will be okay. So suppose that you want to try the left one here. Okay. If you would like to, I think it's still okay, because the squared is not that complicated. So if we take this 2xy minus half y squared and then put this 2, and I still have the x, and we will have, I think, a long equations, but still doable. 2x okay, and I think I will leave this continuation to you. Also, try the polar one. Okay, so that's number 27. How about from the 31 to 40? Yeah.
In addition, axis can be also be symmetric. So
In what?
in xy axis can
Uh-huh.
also be symmetric. So
Basically, yes. Basically, yes. Yeah. As long as you know that it is symmetry. Okay. Okay, for number 31 to 40, any requests? Or maybe let's move to polar for a while, and maybe we could look back if we have another questions. Okay. Okay, maybe we move on here. Maybe from 13 to 16, or perhaps from 17 to 20. Any requests? Yeah, which number? Have you tried before? No, right? No, right? 17? Okay. Okay, we have a picture that we have the 1 minus cosine theta and 1 plus cosine. This is the cardioid, if you are still remembering the name. The cardio, basically they are mimic the heart, the cardio. Right? Okay, the area, okay, for the region D, for number 17, they are in between of this two polar. Okay, these two polar. And because they are symmetry, okay, sometimes in polar, it will easier to see that if this is symmetry. Okay, if we see this, okay, in more details, this shape here. If we just take this and then look at this one side, so we have this is 4 times, right? 4 times. So if we, the whole thing of the D is this piece multiplied by 4, right? Okay, we could see that. So the question is use double integral to find the area. So this is applications on the double integral. So the area in the double integrations, okay, the area is double integral d and then the a, right? This. Okay. Now if we look on this one, let me make red. Okay, this region on red, it starts taking the theta is from theta equals 0, right? From this side here. And then it's move, go here, and this will be theta equal pi over 2. And of course, if we would like to confirm all the things, you can try to check some other values. For example, maybe cosine pi, which will be over here, which it will be -1. So 1 plus 1 is 2, right? So it's supposed that this is twice as much as this. Okay, that's how we confirm. So you can also confirm to this. You can try the cosine of the 3 over 2 pi. Okay, anyway, so we have this is from 0 to pi over 2. So on this, let's say, on this area, the theta is from 0 to pi over 2. And how about the r? And because there is no hole whatsoever, so we could write down this is to pi over 2. And this is, we can say, from 0 to, the red one will be the 1 minus cosine theta. Right? So, total area will be for the area of the small one. So for this will be 0 pi over 2, 1 minus cosine theta, and then the dA becomes r, dr, d theta. So this will be 4, and integrate the r will be half r squared, and plug in so this will be, I will factorize 1 over 2. So r squared will be 1 minus cosine theta squared, d theta. So expand. Okay, and then this is for every polar that you find, the computations or the integrations will be usually involve the square, either cosine or sine, which gives you the idea to take the double angle formally. Okay? So cosine squared, so take the double angle. So this will be half plus cosine 2 theta over 2, right? Okay. And then we have 1 plus this, so this will be 3 over 2 minus 2 plus, let me write this over here, but I hope you can try by yourself. And then take the integrations. This is 3 over 2 theta minus 2 sine theta, and then plus, this will be sine 2 theta over 4. And if you compute this, you will get the 3 over 2 pi multiplied by 2 is so 3, and then we have another one here which is minus 2, so minus 4 2/2 pi, right? Okay. Okay, I think you should try the other questions as well. Calculus will be easy if you just watch videos. But you need to try. You need to try. You need to write something. Okay, that will be different experience. When you watch the videos, it's easy. But when you write, can you do that without looking at the notes? I mean, that is one way to learn. Like, I think there will be many tutorials, and sometimes the tutorials will, we solve this question, and you can pause the video, try first, and then maybe you can ask yourself what kind of questions that you need to ask, like which technique or which formula should I use, blah blah blah, and then play the video, and then okay. And then try again with different questions, maybe the same topic, and see how you can improve. Okay, so you need to challenge yourself. If you're not doing this, if you just watch a video, you think that you're smart, but you're not. That's the problem. Okay, so you need to challenge yourself. Maybe you can set a timer, maybe 5 minutes, 10 minutes for each question, and then start from simple. Start from the very simple one, and then increase your level, and then you are going to know what level you are in, and then when you are experiencing the first-hand practice experience, you know that what you need to learn more. Like, I still need to learn about this topic, and then you can through that topic, and then you can improve. This is something that is very, I think for me, it's common sense. But I don't know why I didn't see from this students. This is very common, even for me. Like, I'm in generations like in the 90s, 2000s, and we still do the same thing. But I don't know why this generation, you're watching too many videos, too many TikTok, too many Instagram, and then you're becoming lazy. Try. If you don't try math, you are not learning math. You're just watching, and then you feel you are smart, but you're not. Okay, this is just how to improve. Okay, how to improve. And since next week will be the final week, so I hope you can improve your study within this few days. Hopefully it helps. Okay, hopefully it helps. If you are taking the next semester, the engineering of math, and if there is no change, you're going to meet with me again. So bear with me and improve your study. And all the calculus stuff, we're going to use it without any explanation. Okay? So I hope you get it in calculus 1 and 2. Okay, anyway, since now it's already 2:55,